Hello everyone, welcome to the lecture 6 of blockchain lecture series. Uh, this lecture will discuss about blockchain interoperability or basically cross-chain messaging and bridging. So let's start with the lecture. What is cross-chain interoperability? Basically cross-chain interoperability enables us to communicate between the blockchains. It allows us to send messages between the blockchains, send assets between the blockchain. Basically, in short words, it allows us for the efficient communication and handling of various types of programs and contracts between various blockchains. A basic application of cross-chain interoperability is cross-chain bridge. Cross-chain bridge is a type of protocol which allows you to transfer your assets between various types of L1s, L2s, and other types of chains which are not abstracted together. So by assets, I mean your tokens, your NFTs, and all. So why cross-chain bridging is needed? So basically, when all the blockchains are made, all L1s and L2s, they are made such that their consensus algorithm allow them to only work inside of a particular chain. So if you are willing to operate inside of a particular chain, you will face no problem to send assets to other addresses and all, to send your NFTs and all. But whenever you will try to send your asset between different chains, between different L1 or L2, or now even L3, you will face problem because no native form of advancement or a technical aspect has been considered while developing a consensus. So consensus specs of any blockchain do not have native support for cross-chain messaging and transfers and all. So that's why blockchain bridges and blockchain communication technology is currently highly needed to engage seamless communication between the chains. So how do they work? So there is a cross-chain integrity. In cross-chain integrity, there are two things to consider. The first one is cross-chain messaging protocol, and a subset of cross-chain messaging protocol is cross-chain bridging. So we will first explore how cross-chain bridges work, and then we will delve into a higher, deeper stack called as cross-chain messaging protocol. The basic idea behind a cross-chain bridge is the interlocking and enabling of assets across various chains. So basically, if you want to send assets between different chains, a smart contract will be deployed on chain A, and a smart contract will also be deployed on chain B. Smart contract, if you want to send your asset from chain A to chain B, smart contract will on chain A will lock your assets on chain A, and it will unlock your assets on chain B. We will discuss this bridges deeper because this can be considered in three types further. So this native form of cross-chain bridges can be classified further into three types: lock and mint, burn and mint, and lock and unlock. So lock and mint, basically, if you want to send a asset from chain one to chain two or chain A to chain B, so smart contract or chain A will lock your asset on chain A and will deploy the wrapped version on an asset on chain B and will mint this wrapped version to a wallet on chain B. So this is a form of lock and mint architecture. Second architecture is called burn and mint. So basically in burn and mint, the contract on chain A will burn your asset and the contract on chain B will mint your asset. So same asset gets burned and minted on different chains. The third form is lock and unlock. So basically, it's similar to burn and mint, but basically it will not burn a uh, already generated asset or mint a new asset. It will just lock already generated asset on your chain A, and it will unlock the same asset on chain B. And this is how a cross chain bridge will work in three different forms. Now, as you can see, when a action has been done on chain A, and then action is followed on chain B. So chain B has to know whether this action was completed on chain A or not. So we can see here that cross-chain bridging is basically a subset of a higher level protocol called as the cross-chain messaging protocol. So cross-chain messaging protocol not only allows you to send your assets, but also allows you to send different threads of messages such as payloads, data packets, and all in the form of call data. And this is a higher form as compared to cross-chain bridging. Now we will explore how cross-chain messaging is currently conducted in various types of protocols and how are we gonna make it more advanced so that the user experience becomes more seamless. So currently, from my research, I have listed five of the top cross-chain messaging protocols which exist now. These messaging protocols are widely used by various application layer protocols to enable cross-chain messaging inside their dApps and application layer. So the first one is the inter-blockchain IBC, inter-blockchain communication IBC. This is the foremost and the most earliest form of cross-chain messaging protocol developed, and currently still it's the most advanced form because it leverages the Cosmos stack for intercommunication. Recently, Chainlink launched the CCIP, which is also a very good stack for cross-chain communication. And the most advanced cross-chain messaging is currently done by Layer 0. We will discuss all these things in the upcoming slides. And apart from that, there is a general message passing body which is made by XLR, and there is a wormholes bridge which uses ZK technology for cross-chain messaging and bridging. So we considered three types of cross-chain bridges earlier, which is according to the architecture they followed. There is lock and mint, burn and mint, lock and unlock, and all. But to classify cross-chain messaging protocols, we need a broader types. To understand this classification, let's consider an example. For example, Alice want to send 5 USDC from chain A to chain B. So first, she will initiate a transaction on chain A. Then she will has to communicate that the transaction has happened on chain A to chain B, and then chain B will initiate the transaction which has to be conducted on chain B. For example, Alice want to uh, burn asset from a vault at Chainway and mint this asset on a vault on Chain B. So it will follow the same example. Asset Alice will burn asset on Chain A, and then a message has to be delivered to Chain B that Alice's asset has been burned on Chain A, and then Chain B has to act when this message has been passed. So, to classify the cross-chain messaging protocol, the main distinction lies how this message is passed from chain A to chain B. So, the first and the foremost method is the method of external validators. There are external validators who continuously monitor the network, and they verify whether the proper action has been taken on chain A, and if the proper action has been taken on chain A, they convey to chain B that the action has been already done on chain A, and you can proceed with your action to complete access transaction. The second method is the transfer of complete blockchain data, block data, and transaction has from chain A to chain B, so that there is no need of external validator, and chain B can itself conduct its own verification to see whether the action on chain A has been completed and then proceed with its own action. So let's discuss these types in more detail. So let's consider first this is the external validator. So this is same what I have told. External validator concept lies on the external validators to verify the data on origin chain, whether the particular action has been conducted on origin chain or not. And then these validator, after validating this data, they convey to chain second chain that the action has been performed, and you can proceed. So in external validators category, there are three further classifications, or not classification, we can say three further types of application which are currently being used in making cross-chain bridging protocols. The first one is centralized bridges. So we will discuss the what happened in centralized bridges is that let's take an example of wormhole. So wormhole contain external network, not network, individual validators, which validates the action on between chains, and then they convey their validation result to the source, the next the target chain. So in a wormhole network, these validators are called as guardians. and they called signal called as VAA, which is the aggregated signature, and this signature is passed to target chain, and the target chain then verify whether the signature is correct or not. So the problem with this architecture is that we are relying on an external validator called as guardian. If this validator is malicious, then chain B can be tricked into considering that a particular transaction has occurred on chain A, even though it has not, and this compromises the decentralization of the network. So to improve on this, a further method was developed called as the middle chains. So middle chains dwell on the concept of centralized bridges only, but what they do is they create a network of validators, so not a single validator. So basically, they deploy their own chain for settlement. Let's consider an example of Seller Bridge. Seller Bridge has deployed its own L1 called as State Guardian Network (SGN). So this is the network of validators. So what this network do is that you can deposit your assets in the new settlement layer, and the validator in this network verify particular user transaction using voting, which is token based voting. They use the seller coin on this network, and if the two-thirds of the votes have been passed, they pass the signature, and then the second transaction can be committed on any chain because the previous chain signature are already passed by the validators. The problem with this is that there will this model will face two types of problem. For example, if the number of validators are low in this middle chain, then again we will be forced with centralization risk. And second is the when the token liquidity is very low. For example, in the current seller bridge, we can see that from the data there are only 20 validators, and the seller token liquidity is about 120 million. So if we considered about one third, which is the 36 million around, so if any of the validator has access to 36 million of the seller bridge tokens, he he or she can directly commence a attack, majority attack. So this is the problem with middle chains concept. So the next protocol which was designed was the bonding protocol. Bonding protocol, we can consider an example of Hawk protocol here. So in bonding protocol, user incentivization has been considered in place of validators. And whenever a validator violates their condition, they are posed with the risk of slashing. So basically in Hawk, we call these validators the bonder. The bonder is supposed to stake some of their assets for before they stake their assets, and bonder is responsible for verifying the communication between chains. For example, Alice has sent a transaction from Arbitrum, so bonder will see whether this transaction has been committed successfully, and then it will tell to Ethereum that this transaction on Ethereum has been conducted. You can deposit Alice's assets in the wallet on Ethereum chain, and then the Ethereum will consensus mechanism will deposit the assets on the LSS wallet on Ethereum chain. So, so this is a basic slashing and staking mechanism used by the Hop protocol or bonding protocols. So yeah, this was the first method called as external validators. Now let's move to the block header and transaction proof. So what happens in block header and transaction proof is that uh, we are not depending on an external set of validators to convey messages from one protocol to another because they possesses decentralization risks. So instead, we take the approach of light clients. So in simple words, what are light clients? Light clients are not while light clients are not full-fledged nodes. Well, light clients just take data from blockchain and locally verify it. They are not run by anything. Anyone can run them. They just take data from all chains and then verify them on chain. And for so basically, light client is a lighter version of full nodes. They do not have to download complete data and are responsible for maintaining the network. They are just verifying the data. Yeah. So the best example of light clients is the IBC protocol, which I discussed earlier. So let's discuss how this IBC protocol works. So you have your chain A and chain B. So chain A's light client will be deployed on chain B, and chain B's light client will be deployed on chain A. So for example, a transaction has been happened on chain A. So this transaction data will be passed to the relayer, and a Merkle proof of this transaction will also be passed to the relayer. The relayer has this transaction in the form of packet and a Merkle proof of this transaction as well. Now, what will happen? This light client of chain A, which is deployed on chain B, uh, this will this will receive the data packet and Merkle proof from the relay. And light client of chain A is responsible for tracking changes on chain A. So it will see with this, it will verify this Merkle proof by considering a commitment hash from the block of chain A. And if the light client of chain A comes to a conclusion that yes, the transaction has been successfully happened, it sends a message to like it's deployed on chain B only. So chain B knows that chain A's light client has successfully verified the data. The chain B will commence with its own part. So this is how light client architecture works. So the main problem of deploying, main problem of light client architecture is that the deploying of light client is very costly. Like this is the IBC light client. It basically works on Tendermint architecture, Tendermint like only on those chains which are developed using Tendermint client. So for example, there is a Cosmos chain or Tendermint chain and a Ethereum chain. So and we want to do a communication between these two chains. So, for example, a transaction has to be sent from Cosmos to Ethereum. So, a light client of Ethereum need to be deployed. Light client of Cosmos need to be deployed on Ethereum, and this light client will be responsible for validating the transaction on Cosmos. So, for example, the Cosmos chain has 100 validators, and the light client which is deployed on Ethereum will be responsible for validating transactions from all these 100 validators. And it's each verification is done using ED 15599 signature scheme. And the verification cost of ED 15599 signature scheme is about 500,000 gas on Ethereum. So if 100 validator signature scheme need to be verified, so about 5 million gas would be required to just validate a single transaction which is communicating from Cosmos to Ethereum. So this is not feasible. The Lightning architecture between Cosmos and Ethereum, because Ethereum does not have a pre-compile of ED 15591 signature directly inbuilt in the consensus. So Lightning architecture can be used efficiently between only Cosmos chains which are developed using Tendermint stack. So this is the Lightning architecture which is used for communication between chains. So this was all about cross-chain messaging and cross-chain bridging protocols. Now, what is the current researches which we are doing in this space? The next part of this will be, or the next phase will be the chain abstraction. Chain abstraction is basically, in simple words, there will, it's you can see there are thousands of L2s and L3s coming right now, and L1 as well. So, main goal of chain abstraction is there will be no chain at all. Everything will be unified, and user don't have to even know about that assets are transferred between various types of chains. For user, from user's perspective, it will be a single USDC coin traveling around anywhere. So I will discuss briefly very few approaches which are currently being considered for developing chain abstraction part in the blockchain industry. Yeah. So Near's approach is currently live. What Near Near has uh, Near has enabled their nodes to uh, understand the signature of various EVM and non-EVM chain through multi-party computation scheme. So basically, in Near you have a single account, and through this single account you would be able to uh, so, Yeah. So so basically you will have a single account, and this single account will be responsible for generating signature, which is compatible on various types of chain, and the nearest native nodes will be responsible for aggregating this signature and understanding this signature scheme using multi-party computation. And once this signature has been generated, a single account will be able to uh, communicate various transactions to various types of chain. So MPC is the current architecture utilized by DM. And second one is Polygon's aggregation layer. The aggregation layer went live recently only, 3 to 4 days back. So Polygon's aggregation layer basically relies on the fact that all the chains which are developed using the CDK, cross-chain development kit, would be able to use a unified layer for communication. This tech stack basically aggregates the GK proofs across all the chains built using CDK and aggregate them and submit a unified proof on the Ethereum chain. So GK proof aggregation is the basic concept inside of Polygon's aggregation layer, which will bring interoperability between the chains which are developed using Polygon CDK. Optimism superchain utilizes the same concept as the Polygon's aggregation layer. Brings interoperability between the chains which are developed using OP stack. And instead of the ZK proof aggregation, OP stack depends on the optimistic proof aggregation between all the chains which are developed using OP stack. Yeah. So the foremost concept is the omni-chain network. Uh, Omni-chain network is the current research going on in the interoperability space. Basically, the particle network has developed the omni-chain framework. So inside OmniChain, you have a separate chain which is responsible for settling all transactions which are currently going on other chains. So in particle network, you have a universal account and a universal liquidity layer, and everything will be utilized from this account and liquidity layer across various protocols. So the liquidity fragmentation is currently solved using OmniChain network. So this is the briefing of current four methods currently going on. So in near is live, OP chain is in concept stage, Polygon aggregation layer went live few days ago, and particle network is in testnet development. So the primary offering for near is account aggregation which is using MPCs. OP and Polygon will be only focused on their own native L2s, and particle network will be uh, it's basically a universal settlement layer, like a separate consensus mechanism for all chains to settle their transaction. Near will cover all chains, particle will cover all chains, OP and Polygon will be only focused on their stack, and their primary method has also been displayed here. Yeah. So chain abstraction is the final and the foremost steps which we are currently trying to achieve in the blockchain space. So basically, let's take an example of chain abstraction. Like you have a wallet, you have 100 USDC, and wallet you need to send 100, like you have 100 USDC, even though there are 30 USDC on Ethereum, 20 on Arbitrum and all, but the user will never know how this distribution is conducted. User will just see that his wallet contains a 100 USDC account balance, and he or she can send it to anyone, uh, and she or does not have to worry about any chain. So this is basically the concept of chain abstraction, and we are trying to reach it. Yeah, thank you. Yes, yes.